Okay, so now I would like to invite Khushi Parween. Khushi is pursuing BSc in Mathematics from Vinod Bihari Mehto Oriental University, Dhanbad, and her topic of presentation is Riemann's criterion for integrability. So, Khushi, over to you.
So, hello everyone. I'm going to present my topic about Riemann criterions for integrability. So, before going to prove my theorem, we will see some important definitions which are important part of our theorem. So, look at the first definition, which is what is partition. A partition or subdivision P of an closed interval AB is a finite set x naught x1 dot xn such that a equals to x naught less than x1 less than dot less than xn minus 1 less than xn less than b. The points xi are called the knots of p. This is a definition of partition. Next, we look at the another definition, Darboux sums, which is upper Darboux sum and lower Darboux sum. So for defining, we start with let a function f be real bounded function defined on closed interval AB and P be the partition of closed interval AB and x naught x1 x1 x2 dot xi minus 1 xi plus 1 dot close interval xn minus 1b are subintervals of closed interval AB. And from this, we say that lower Darboux sum is summation from I is equal to 1 to n mi xi minus 1, which is equal to summation I is equal to 1 to n mi delta I, where delta I is the length of the subintervals and where mi is the infimum of function in the subinterval xi minus 1 xi, and the lower Darboux sum is denoted by LFP. And upper Darboux sum, if mi is the supremum of function in subinterval xi minus 1 xi and delta I is the length of the subinterval, so S is equal to summation I is equal to 1 to n mi xi minus 1 is equal to summation I is equal to 1 to n capital Mi delta I, and is denoted by UFP, which is upper Darboux sum. Let us look at the geometrical interpretation of this definition. If f is positive function, then the lower sum LFP can be interpreted as the area of the union of rectangles with base xi minus 1 xi and height mi with base xi minus 1 xi. And if mi is the mi is the supremum, then the geometrical interpretation of the upper sum is the area of the union of rectangles with the base xi minus 1 xi with height capital Mi, which is supremum. So this is our geometrical interpretation. Now with one more important definition which is used in our theorem, lower Riemann integral. Let f be a bounded function defined on closed interval AB. We know that the numbers LP increases as the partition gets finer and finer, and the set of numbers LP with respect to all partitions P of closed interval AB is bounded above by MB minus A. Hence, there exists a least upper bound for the set LP. Where, the least upper bound of the set is defined as the lower Riemann integral of f over closed interval AB and is denoted by LF, which is equal to least upper bound of set LP, where LUB is taken over all partitions of closed interval AB. Next is upper Riemann integral. Similarly, the numbers UP decrease as the partition P gets finer and finer. And the set of numbers UP with respect to all partition P of closed interval AB is bounded below by MB minus A, where M is the infimum, and hence there exists the greatest lower bound for the set UP. The greatest lower bound of the set UP is called the upper Riemann integral of f over closed interval AB and is denoted by UF, which is equal to greatest lower bound of UP, where GLB is taken over all partitions of P, partitions P of closed interval AB. For simplicity, we sometimes denote the lower and upper Riemann integrals of f over closed interval AB by integral a bar to bf and upper integral as a to integral a to b bar f respectively. Now we are going to prove my theorem. So the theorem states that let f be a bounded function defined on closed interval AB, then f belongs to RAB, that is f is Riemann integrable. If and only if for every epsilon greater than 0, there exists a partition P of closed interval AB such that oscillatory sum, which is upper Darboux sum minus lower Darboux sum, is less than epsilon. So I am going to prove sufficient. So proving this theorem, we start with let I1 and I2 be the lower and upper integrals. Suppose that for every positive epsilon, there exists a partition P of closed interval AB says that upper Darboux sum minus lower Darboux sum less than epsilon. This is our given condition. We are assumed that the condition is satisfied. Now by the definition of lower and upper integrals, we have I1, which is our lower integral, is greater than equals to lower Darboux sum, and upper integral is less than equal to upper Darboux sum. Here I write I1 is greater than equals to lower Darboux sum because I1 is the greatest lower bound of I1 is the least upper bound of lower Darboux sum, and I2 is the least upper bound of upper Darboux sum. So here we write like this. Next from equation 1 and 2, we subtract I1 and I2, then we get I2 minus I1 less than equals to upper Darboux sum minus lower Darboux sum less than epsilon, which implies that I2 is less than I1 plus epsilon. Since epsilon is arbitrary, so it follows that I2 is less than equal to 1. So, but we know that lower R integral cannot exceed the upper R integral. So hence from equation 3 and 4, this implies that I1 is equal to I2. Therefore, f is Riemann integrable, as we have proved the sufficient condition, that the condition is sufficient. Now, the necessary condition has to be proved. Let epsilon greater than 0 be given, and let I1 and I2 be the lower and upper Riemann integrals as usual. So let f belongs to RAB. Here, function is Riemann integral, so that I1 is equal to I2. From the Riemann condition of integrability, we know that lower Riemann integral is equal to upper Riemann integral. Since I1 is the least upper bound of lower Riemann sum for all partitions P, there must exist partition P1 of closed interval AB says that I1 minus epsilon by 2 is less than lower Darboux sum. This is from Darboux theorem of integrability. And this also implies that I1 minus lower Darboux sum is less than epsilon by 2. Similarly, since I2 is the greatest lower bound of upper Darboux sum for all partitions P, so there must exist a partition P2 of closed interval AB such that upper Darboux sum is less than I2 plus epsilon by 2, so that we can write it as upper Darboux sum minus I2 is less than epsilon by 2. Now let P is equal to P1 union P2, which means P is the common refinement of both P1 and P2. We have if all the refinement is if all the partitioning points of P1 as well as P2 are also the partitioning points of P. So here if since P is a refinement of both P1 and P2, so we have lower lower Darboux sum with respect to partition P1 is less than equal to lower Darboux sum with respect to partition P, and we know that lower Darboux sum is always less than upper Darboux sum. From the geometrical interpretation, we can easily see that. And upper Darboux sum is less than, with respect to partition P, is less than equal to upper Darboux sum with respect to partition P2. Now, contribution to the oscillatory sum, that is upper Darboux sum minus lower Darboux sum, is equal to upper Darboux sum minus I2 plus I2. Here I am adding and subtracting I2, which is and minus LFP, which is equal to upper Darboux sum minus I2 plus I1 minus low minus lower Darboux sum, which is less than equal to. Here I change I2 to I1, since I1 is equal to I2 as I stated earlier. So this is less than equal to upper Darboux sum with respect to partition P2 minus I2 plus I1 minus lower Darboux sum with respect to partition P1 by equation 7. This is less than epsilon by 2, as here I mentioned this is less than epsilon by 2, and this is also less than epsilon by 2. So their sum is less than epsilon by 2 plus epsilon by 2, which is equal to epsilon. So the contribution to oscillatory sum is less than epsilon, which means the condition is necessary. Thus the theorem is proved. Now I am going to present example as application of this theorem. So here we consider a function fx which is equal to x square on closed interval 0, 1. So let epsilon greater than 0 be given. So choose a partition P such that max of xi plus 1 minus xi such that I lies between 1 and n minus 1, which is less than epsilon by 2. The max of this is less than epsilon by 2. Since f is increasing, so we obtain infimum of f is equal to function of xi is equal to xi square from the definition of our function, and supremum of f is equal to function of xi plus 1, which is equal to xi plus 1 square. Now it follows that contribution to oscillatory sum UFP minus LFP is equal to summation I is equal to 1 to n xi square xi minus 1, which is by the definition of upper Darboux sum, and minus summation I is equal to 1 to n xi minus 1 square xi minus 1 from the definition of lower Darboux sum. Here xi square is the infimum, and xi minus 1 is the supremum of the function, which is equal to summation I is equal to 1 to n xi square minus xi minus 1 square. Here I am taking xi minus 1 as common, which is equal to summation I is equal to 1 to n xi minus 1 xi plus xi minus 1. Here I will distribute this. Here I break this into two parts, xi minus 1 and xi plus xi minus 1. This is as it is, which is less than summation I is equal to 1 to n, and as we have given that this is less than epsilon by 2. This is less than epsilon by 2. So here we write less than epsilon by 2 into, and this is written as 2 because xi plus 1 lies between the interval 0 to 1. So their sum is 2, and xi minus 1 is written as it is, which is equal to epsilon. Since this is epsilon, summation I is equal to 1 to n xi minus 1. This is equal to 1, which is length of the subinterval, which is our 0, 1. Length of the subinterval is 1. So this is equal to epsilon. Hence, by the Riemann criterion for integrability, the example is hence f is integrable. Now I am going to prove this theorem, which is the important application of that theorem as I proved earlier. So this theorem states that if f be continuous on closed interval AB, then f belongs to RAB, that is f is Riemann integrable. Now before starting proof, we will consider that P be the P is equal to x naught x1 dot xi minus 1 xi dot xn is equal to B. Be any partition of closed interval AB with the norm mu p less than delta. Norm is the maximum of, that is greatest of the lengths of subinterval, is the norm of the partition, which is maximum of the lengths of subinterval. So let xi minus 1 is equal to delta I, which is length of the subinterval. I lies between 1 to n. Since f is continuous on closed interval AB, therefore it is uniformly continuous on that interval, and as per the definition of the uniform continuity, to every epsilon greater than 0, there exists a delta greater than 0 such that mod of fx dash minus fx double dash less than epsilon dash for all for all points x dash x double dash belongs to closed interval AB. Whenever mod of x dash minus x double dash is less than delta, this is from the definition of the uniform continuity. Again, since f is continuous on closed interval AB, so it is bounded on closed interval AB because every continuous function is bounded and attains its infimum and supremum on closed interval AB. And so on every closed subinterval of closed interval, it also attains infimum and supremum on every closed subinterval of closed interval AB. Let f attains its infimum small mi and supremum capital Mi at some points alpha I and beta I. That is, f of alpha I is equal to mi and f of beta I is equal to capital Mi. Now alpha I, beta I belongs to the closed subinterval xi closed in subinterval, that is comma. So xi minus 1, where xi minus 1 less than delta, because this is length of the subinterval, as I have written earlier. Therefore, alpha I minus beta I is less than delta. Now, hence it follows from 1. So it follows from 1 that f of alpha I minus f of beta I is less than epsilon dash. That is, mod of mi minus capital Mi is less than epsilon dash infimum minus supremum. Mod as we can replace the mod and write as mi minus small mi less than epsilon dash. We'll use this. Now, contribution to oscillatory sum, which is upper Darboux sum minus lower Darboux sum, which is equal to summation I is equal to 1 to n mi delta I minus summation I is equal to 1 to n mi delta I, which is equal to summation I is equal to 1 to n mi minus mi and delta I taken as common less than epsilon dash summation delta I, since delta I is the length of the subinterval closed interval AB. So delta is the length of closed interval AB. So delta is equal to B minus A, which is equal to epsilon dash B minus A. Now, writing choosing epsilon dash is equal to B minus A in equation, and writing in equation 3, then we get epsilon upon B minus A into B minus A is equal to, actually this is epsilon upon B minus A into B minus A is equal to epsilon. Hence f belongs to R closed interval AB, that is f is Riemann integrable. Hence that statement is proved that every continuous function is Riemann integrable. These are the references which I used in this theorem, and some application of this theorem in real life is in integration as well as differential calculation. We use this. They are applied from calculus to physics problems. It is also used for measurement of distance traveled by some object, because we can easily retrieve the average velocity versus time graph. The distance traveled is represented by the area under the given curve. This is also used in partial differential equations and representation of function by trigonometric series. Also having such few applications, the Riemann integral is quite challenging to handle, as we can see that its definition is little sophisticated, so it is bit inconvenient to use in practical life. So this was my presentation. Thank you.
Okay, thank you, Khushi. So, are there any questions?
I have a
Yes, anyone?
question.
Yes,
I have a
Chirag.
question. So, Khushi, you've used the Riemann criterion over here to do a few positive proofs. Can we use it somehow to perhaps prove that something is not Riemann integrable? So, for example, something like, say, the Dirichlet's function.
Can you repeat the question?
Right. So, my question is that you've used Riemann's criterion over here to prove something like a lot of positive proof that is, this is integrable, this is integrable. So, for example, continuous maps are integrable. Continuous functions from closed interval AB are integrable, for example. Uh, is it possible to prove this is not something is not Riemann integrable? So I'm sure you're aware of, say, the Dirichlet's function, which is not Riemann integrable. So can we use Riemann's criterion to justify that? I'm looking for example, a contradiction proof.
Uh, Khushi, are you aware of Dirichlet function? Maybe it's zero in irrational and one
One on
in rational.
rationals.
Yeah, over 0 1, closed interval 0 1. That is the
Yes.
function.
Yes, sir.
Yeah, can you say something about its integrability, Riemann integrability? Maybe go to your definition where you prove the statement. That you go to that statement. Yeah. So here, what you are trying to say that it will be remain integrable if for given epsilon greater than 0 if your UFP minus LFP is less than epsilon, right?
Yes, sir.
So in your function, what we have given is it is 0 on irrationals and 1 in rationals. So now you divide into n parts, 0 1, close interval
Yes,
0
sir.
1, you divide into n parts.
Yes, sir. I get it. Here, matlab,
Okay.
here is the function is defined by 1 if x is rational and 0 if x is irrational.
Yeah.
So clearly f is bounded function over closed interval AB. So
Okay.
we have to show that it is not Riemann integral over closed interval AB. So we
Mm-hmm.
can let the partition P be any partition of closed interval AB, and as usual, we let that MI and capital MI denote the GLB and LUB respectively. So
Mm-hmm.
and let M and capital M be the greatest lower bound and least upper bound of F in closed interval AB. Then M is equal to 0 and capital M is equal to 1 because this is bounded function, and is 0 is the uh, 0 is the infimum and 1 is the supremum. Since every subinterval xi minus 1 xi of closed interval AB, which means contains rational as well as irrational points. So
Correct.
now upper sum is equal to summation I is equal to 1 to an mi delta I, or here mi, our mi is 1 and delta I is equal to mi 1 into summation I is equal to 1 to n delta I is equal to 1 since our supremum is 1 for each I. So our length of the subinterval is 1. So 1 into 1 is equal to 1. So upper sum is equal to 1. And similarly, we get lower sum by applying the same formula. Summation I is equal to 1 to n mi delta I. So 0 is the our infimum. So its lower sum is 0, and lower sum and upper sum, lower sum is equal to 0 and upper sum is equal to 1 for every partition P of closed interval AB. Hence, least upper bound of set of lower sum is equal to 0, which is lower Riemann integral, which is 0, and greatest lower bound of the set upper sum, uh, which is upper integral. So this is equal to 1. And since this is not equal, which means least upper bound of LP and greatest lower bound of upper sum not is equal, lower integral and upper integral are not equal. Therefore, F is not Riemann integral over closed interval AB, although it is bounded over closed interval.
Yeah, so this equal thing you have not stated, na? You have stated only that difference should be less than epsilon.
Yes,
Anyway, though those are equivalent, but you can say like your UFP is 1, your LFP is 0.
yes,
So you are free to choose your epsilon greater than 0. You can choose epsilon to be half. Then 1 is less than half. That doesn't work. No?
yes, sir.
Yeah, that way you can say. So, okay. Chirag, is it okay?
Yes, I understand the proof. Thank you so much, Khushi.
Yeah. So, another thing, like maybe viewers can check it out. Like it is not Riemann integrable. What next? I mean, can we integrate it? If so, then how? So here comes the trick. Like you can explore what is Lebesgue integral now. After Riemann integral, where Riemann integral fails, so Lebesgue has come out with his ideas to rectify it. So Khushi, can you go to the where you have defined UFP and LFP?
Yes, sir.
Yeah, yeah. So here, like you can see, uh, this partition xi minus xi minus 1, like x1 x0 x1 dot xn, this thing. So we have taken a partition of closed interval 0 1 into n parts, where each one are intervals. So in Lebesgue integral, we are taking like disjoint sets. We will be taking disjoint sets. I mean, you can explore. I am giving some hints only. So we can have disjoint sets, and Lebesgue has developed a machinery called measure to measure a set. I mean, how much measure it has. For example, in intervals like say closed interval AB or open interval AB, both have B minus 1, B minus A as its measure. So similarly, for any interval, and even for discrete closed sets, open sets, I, for most of the known sets, the measure is there. There is a machinery how to define measure. So as long as you can define a measure of a set, then you can multiply like what are the values at those sets. You can multiply and sum. This is the technique like what Riemann did here. Like s equals to I equals to 1 to n. He is multiplying value at some point, at some set like xi minus 1. That means in that interval the value is mi. So in similar fashion, there also in a set it has a measure, that measure into average height at that set. That kind of thing is there. So you can explore it, uh, explore Lebesgue integral. Yeah, I'm done, Jyoti.
Okay, so any other questions? Okay, fine. So we can end this presentation here. Thank you, Kushi.